Hello everyone, welcome to this video where we'll explore a key question in the world of Apache Spark. What are the different cluster managers available in Spark and how do they affect PySpark applications? Cluster managers are a critical part of distributed computing as they handle resource allocation, task scheduling, and scalability for Spark applications. In this video, we'll break down the different cluster managers, standalone yarn, Mesos, Kubernetes, and local mode and discuss their unique strengths, weaknesses, and impact on PySpark applications. Let's dive in. Introduction. Apache Spark is a robust distributed computing framework that excels at handling big data processing across clusters of machines. Its ability to distribute tasks efficiently makes it a key tool in modern data engineering and analytics. A critical component of Spark scalability and performance is its integration with cluster managers, which coordinate resources and tasks across the cluster. These managers ensure that Spark applications utilize computational resources effectively, enabling seamless operations in distributed environments. What is a cluster manager? A cluster manager is a vital component in a distributed computing environment responsible for efficiently managing resources and coordinating tasks across a cluster of machines. In the context of Apache Spark, the cluster manager plays a critical role in ensuring that Spark applications can run seamlessly and utilize the available computational resources effectively. The primary responsibilities of a cluster manager include resource allocation and task scheduling. Resource allocation involves distributing resources like CPU and memory to Spark applications based on their requirements, ensuring that multiple applications can run concurrently without resource contention. Task scheduling, on the other hand, ensures that jobs are distributed across worker nodes, breaking them down into smaller tasks and managing their execution. This process helps achieve parallelism and maximizes the performance of Spark applications. By abstracting the complexities of resource management, cluster managers enable Spark to focus on executing tasks efficiently, making them a cornerstone of Spark's ability to handle large-scale data processing. Examples of popular cluster managers include Spark's built-in standalone cluster manager, Apache Yarn, and Kubernetes, each offering unique features to meet different deployment needs. Importance of cluster managers. Cluster managers are a cornerstone of distributed computing frameworks like Apache Spark, playing a critical role in ensuring efficient and reliable operation. Their importance lies in several key responsibilities that directly impact the performance, scalability, and fault tolerance of Spark applications. First, resource allocation is a primary function of cluster managers. They determine how computational resources, such as CPU and memory, are distributed among multiple applications running on the cluster. By doing so, they ensure that all applications receive the resources they need to execute efficiently while avoiding conflicts or overloading. Second, cluster managers provide fault tolerance, which is crucial in distributed environments where failures are inevitable. If a task or a node fails during execution, the cluster manager detects the failure and reschedules the task on a different node. This ensures that the application can continue running reliably without manual intervention. Third, cluster managers enable scalability by managing resources dynamically as workloads grow or shrink. They can scale the cluster to accommodate small jobs efficiently and expand resources to handle large-scale workloads seamlessly, ensuring optimal performance across varying demands. Finally, scheduling is another vital role of cluster managers. They queue and prioritize tasks to maximize resource utilization and minimize execution time. By intelligently scheduling jobs, cluster managers enhance the overall efficiency of the system, allowing multiple applications to share the cluster without significant delays or resource contention. In summary, cluster managers are indispensable for resource management, fault tolerance, scalability, and scheduling, making them a fundamental component of any distributed computing framework like Apache Spark. Choosing a cluster manager. Choosing the right cluster manager is a critical decision when setting up a distributed computing environment with Apache Spark. The choice depends on several factors, including the workload, infrastructure, and application requirements, as each cluster manager offers unique features and benefits tailored to specific scenarios. First, the workload plays a significant role in selecting a cluster manager. For small scale or less complex tasks, Spark's standalone cluster manager may be sufficient, offering simplicity and ease of setup. However, for large-scale resource-intensive workloads that require advanced scheduling and fault tolerance, more robust options like Apache Yarn or Kubernetes are better suited. Second, the infrastructure available in your organization can heavily influence the decision. If your environment is built on the Hadoop ecosystem, Apache Yarn integrates seamlessly with Spark and provides excellent resource management. On the other hand, if your organization uses containerized applications, Kubernetes offers a modern, flexible solution with native support for deploying Spark in a containerized cluster. Finally, application requirements are a key consideration. If your application demands high fault tolerance to handle potential node or task failures, a cluster manager like Yarn or Kubernetes is ideal due to their advanced recovery mechanisms. If resource sharing among multiple users or applications is important, these managers excel at managing multi-tenant environments. Additionally, for organizations prioritizing ease of deployment and management, Kubernetes declarative configuration and scalability make it an attractive choice. In summary, choosing a cluster manager depends on balancing the complexity of your workload, the available infrastructure, and the specific needs of your Spark applications. Making the right choice ensures that your Spark environment operates efficiently, reliably, and at scale. Cluster managers available in Spark. A. Standalone Cluster Manager. The Standalone Cluster Manager is Apache Spark's built-in solution for managing clusters designed to provide a lightweight and straightforward option for running Spark applications. Since it comes bundled with Spark, it eliminates the need for external dependencies or complex configurations, making it an attractive choice for simpler setups. The features of the standalone cluster manager include support for dynamic resource allocation, allowing Spark to adjust the number of executors during runtime based on workload demands. However, resource management in large-scale deployments requires manual intervention, such as specifying the number of nodes and resources explicitly. This lack of advanced automation makes it less suitable for complex, multi-tenant environments or massive data processing tasks. The use cases for the standalone cluster manager are primarily focused on development and testing environments where simplicity and ease of use are critical. It is also well suited for small clusters that do not require sophisticated resource management or integration with external systems. For teams or individuals setting up Spark on dedicated resources with minimal overhead, the standalone cluster manager provides an efficient and reliable option. While it may not offer the scalability and flexibility of other cluster managers like Yarn or Kubernetes, the standalone cluster manager is an excellent choice for lightweight workloads and non-production environments, ensuring Spark applications can run seamlessly without additional infrastructure. B. Apache Hadoop Yarn, yet another resource negotiator. Apache Hadoop Yarn, yet another resource negotiator, is one of the most popular cluster managers for Spark, especially in environments built on the Hadoop ecosystem. Yarn acts as a centralized resource management platform that enables Spark to run alongside other Hadoop applications such as Hive, HBase, and MapReduce, ensuring efficient utilization of cluster resources. The key features of Yarn include its ability to dynamically allocate resources based on the requirements of Spark applications. This dynamic allocation ensures that computational resources like CPU and memory are distributed efficiently, allowing multiple applications to share the same cluster without resource contention. Additionally, Yarn supports multi-tenancy, enabling different teams or applications to coexist in a shared resource environment while maintaining isolation and fairness. Yarn's advanced scheduling capabilities also help prioritize jobs and manage workloads effectively in complex, large-scale setups. Yarn is ideally suited for large-scale data processing environments where Spark is often integrated with other tools in the Hadoop ecosystem. For organizations that already have Hadoop clusters, Yarn provides a seamless way to add Spark workloads without requiring additional infrastructure. Its tight integration with Hadoop distributed file system, HDFS, and other components ensures smooth interoperability and optimal performance. In summary, Apache Hadoop Yarn is a robust and versatile cluster manager that makes Spark an integral part of the Hadoop ecosystem. Its support for dynamic resource allocation, multi-tenancy, and shared environments makes it a go-to choice for organizations running large-scale, multi-application data processing pipelines. See, Apache Mesos. Apache Mesos is a general-purpose cluster manager designed to support multiple distributed frameworks such as Apache Spark, Kafka, and TensorFlow on the same cluster. It provides a unified resource management layer, making it highly flexible and suitable for environments where diverse workloads need to coexist and share resources effectively. One of Mesos' standout features is its fine-grained resource scheduling, which allows applications to request and allocate resources like CPU and memory with a high degree of precision. This granularity ensures optimal utilization of cluster resources, enabling multiple frameworks to run simultaneously without conflicts. Additionally, Mesos offers flexible resource sharing, allowing dynamic adjustments to resource allocations based on changing workload demands, which is particularly useful in environments with varying application requirements. Mesos is ideally suited for multi-framework environments where organizations run several distributed systems side by side on a single cluster. It excels in scenarios that require complex resource sharing and scheduling, making it a powerful choice for research, development, and production systems with diverse workloads. Mesos' ability to manage resources across multiple frameworks also simplifies cluster operations and reduces the need for dedicated infrastructure for each framework. In summary, Apache Mesos is a versatile cluster manager that shines in environments with diverse distributed workloads. Its fine-grained resource scheduling and flexible resource sharing capabilities make it an excellent choice for organizations looking to maximize the efficiency and scalability of their infrastructure while running multiple frameworks in parallel. P. Kubernetes. Kubernetes is a modern, container-based cluster manager that provides robust support for running Spark applications in containerized environments. Designed for cloud-native applications, Kubernetes excels at orchestrating distributed systems and managing workloads using Docker containers, making it a popular choice for organizations embracing microservices architectures. The key features of Kubernetes include dynamic scaling, which allows Spark applications to adjust resource usage in real time based on workload demands. This ensures efficient utilization of cluster resources and eliminates over-provisioning. Another significant feature is workload isolation using containers, which provides a secure and consistent runtime environment for each Spark job. This isolation not only enhances reliability but also simplifies dependency management by packaging application specific libraries and configurations within the container. Kubernetes is particularly well suited for cloud native applications and environments that leverage Docker containers and microservices. Its declarative configuration model enables seamless deployment and management of Spark applications in both on-premises and cloud infrastructures. Additionally, Kubernetes integrates well with modern DevOps practices, allowing Spark jobs to be incorporated into CI/CD pipelines and automated workflows. In summary, Kubernetes is an advanced cluster manager that combines the scalability and efficiency of container orchestration with the power of Spark. Its dynamic scaling, workload isolation, and integration with cloud native tools make it the ideal choice for organizations building modern containerized data processing solutions. E. Local mode. Local mode is a special configuration in Apache Spark that allows Spark applications to run on a single machine without the need for a cluster manager. This mode is simple to set up and does not require a distributed computing environment, making it a convenient option for specific use cases like development and debugging. The primary feature of local mode is its suitability for development and debugging tasks. Since it runs on a single machine, it eliminates the overhead of configuring and managing a cluster, allowing developers to focus on writing and testing their Spark code. This makes local mode an excellent tool for prototyping new ideas, experimenting with transformations, and debugging issues before deploying applications to a larger distributed cluster. The primary use case for local mode is single node testing or local development. Developers often use it to verify the correctness of their Spark logic on small datasets without incurring the cost or complexity of running a distributed setup. However, local mode is not designed for production use as it cannot handle the scalability of fault tolerance required for large scale data processing. In summary, local mode is a lightweight and accessible option for Spark users who need a quick and simple way to test and debug applications locally. While it lacks the scalability of distributed modes, it plays a crucial role in the development life cycle by providing a low overhead environment for early stage experimentation. How cluster managers affect PySpark applications. Cluster managers play a critical role in determining the performance, reliability, and scalability of PySpark applications. They handle various aspects of resource management and task execution, directly impacting how Spark processes large scale data and manages workloads. Let's explore the key ways cluster managers influence PySpark applications. One of the primary responsibilities of cluster managers is resource allocation. They allocate CPU, memory, and other resources to the Spark driver and executors based on the application's requirements. Proper resource allocation ensures that Spark jobs run efficiently without underutilizing or overloading cluster resources. For instance, managers like Yarn and Kubernetes allow fine-grained control over resource distribution, ensuring optimal performance. Task scheduling is another critical function. Cluster managers schedule Spark jobs by dividing them into tasks and distributing these tasks across worker nodes. Advanced managers such as Yarn and Kubernetes enhance this process with features like priority based scheduling and fair resource sharing. These capabilities are particularly beneficial in multi application environments where tasks need to be executed based on urgency or resource availability. Fault tolerance is essential in distributed systems, and cluster managers ensure reliability by detecting and recovering from node or task failures. Managers like Yarn, Mesos, and Kubernetes provide robust fault tolerant mechanisms, such as rescheduling failed tasks on healthy nodes to maintain application continuity and prevent job failures. Scalability is another significant advantage offered by modern cluster managers. Managers like Kubernetes and Yarn support dynamic resource scaling, enabling Spark applications to scale up during heavy workloads or scale down during lighter loads. This capability is invaluable for efficiently handling fluctuating data processing demands and maintaining cost effectiveness in cloud environments. Ease of deployment is a key factor in simplifying PySpark workflows. Cluster managers abstract the complexities of resource management, making it easier to deploy Spark applications. Kubernetes, for example, leverages containerization to ensure that applications are portable and easy to manage across different environments. In smaller setups, the standalone cluster manager provides a straightforward option for deployment without requiring external dependencies. In multi-tenancy scenarios, managers like Yarn and Mesos excel at enabling multiple applications to share resources within a single cluster. They ensure fair resource usage across tenants, allowing organizations to maximize the utilization of their infrastructure while maintaining isolation between workloads. Finally, cost efficiency is a crucial benefit of dynamic resource allocation in managers like Kubernetes and Yarn. By scaling resources up or down based on workload demands, these managers help optimize operational costs, particularly in cloud environments where resource use directly translates to expenses. In summary, cluster managers are foundational to the success of PySpark applications. They provide the resource management, fault tolerance, scalability, and cost efficiency required for handling modern data processing workloads effectively, making them an indispensable part of any distributed computing ecosystem. In comparison of cluster managers, when choosing a cluster manager for PySpark, it's important to understand the strengths and weaknesses of each option as they cater to different needs and environments. Here's a detailed comparison to help you make an informed decision. The standalone cluster manager is Spark's built-in solution, offering a lightweight and easy to set up option for managing resources. Its simplicity makes it ideal for small-scale setups and dedicated Spark clusters. However, it lacks advanced features for scalability and resource sharing, making it less suitable for larger, multi-tenant environments or complex workloads. Yarn, deeply integrated with the Hadoop ecosystem, is a popular choice for organizations leveraging Hadoop distributed file system, HDFS, or tools like Hive and HBase. It excels in fault tolerance and resource allocation, supporting large-scale data processing efficiently. However, its dependency on a pre-existing Hadoop cluster can be a limitation for organizations without Hadoop infrastructure. Mesos shines in multi-framework environments, offering the flexibility to run diverse workloads such as Spark, Kafka, and TensorFlow on the same cluster. It is highly scalable and supports fine-grained resource management, making it suitable for complex multi-application scenarios. However, its configuration and setup are more complex compared to other cluster managers, which can be a hurdle for teams without specialized expertise. Kubernetes is a modern cluster manager tailored for containerized environments. It supports dynamic scaling, workload isolation, and seamless deployment, making it the ideal choice for cloud native and containerized applications. With its ability to integrate with Docker and microservices architectures, Kubernetes offers unmatched flexibility and scalability. However, it requires a solid understanding of Kubernetes concepts, which can be a steep learning curve for teams due to container orchestration. Lastly, local mode is a special configuration for single node execution, making it perfect for development, debugging, and testing. It allows developers to prototype and experiment with Spark applications without needing a distributed setup. However, its functionality is limited to a single machine, making it unsuitable for production or large scale processing. In summary, the choice of cluster manager depends on your specific requirements. Standalone and local mode are great for simplicity and testing. Yarn is ideal for Hadoop ecosystems. Mesos excels in multi-framework environments, and Kubernetes is the top choice for containerized, scalable deployments. Understanding these trade-offs ensures you select the right cluster manager to optimize your Spark applications. Example, PySpark application with different cluster managers. In standalone mode, This example demonstrates how to run a PySpark application in standalone mode, which is Spark's built-in cluster manager. Standalone mode is a lightweight and simple option for managing Spark jobs without relying on external cluster management frameworks. It's suitable for small clusters and dedicated Spark setups. The command Spark submit is used to submit a Spark application to the cluster. In this case, the master flag specifies the master node of the standalone cluster, identified by its URL Spark master 7077. The 7077 port is the default communication port for the Spark master. The master node coordinates the job execution by managing resource allocation and task scheduling across worker nodes in the cluster. The deploy mode cluster option indicates that the Spark application will be deployed in cluster mode, meaning that the driver program will run on one of the worker nodes instead of the machine where the job is submitted. This setup is useful for production environments as it offloads resource management and execution to the cluster, enabling better utilization of the submitting machine's resources. Finally, the my underscore script.py argument specifies the Python script containing the Spark application logic. This script will be distributed to the cluster and executed according to the specified configuration. In summary, running a PySpark application in standalone mode with this command is a straightforward way to utilize Spark's built-in cluster manager for small to medium-sized workloads. It provides a simple and efficient environment for managing Spark jobs without the complexity of external dependencies or advanced configurations. Yarn mode. This example demonstrates how to run a PySpark application in Yarn mode, where Yarn, yet another resource negotiator, serves as the cluster manager. Yarn is widely used in Hadoop ecosystems, offering robust resource management and multi-tenancy for distributed applications. The command starts with Spark submit, which is the standard utility for submitting Spark jobs. The master yarn flag specifies yarn as the cluster manager, enabling Spark to run in an environment where it shares resources with other Hadoop applications like Hive or HBase. This tight integration makes yarn an excellent choice for Spark jobs in Hadoop-based infrastructures. The deploy mode cluster option indicates that the driver program will execute on a node in the yarn cluster rather than on the machine submitting the job. This setup is particularly beneficial in production environments as it reduces resource consumption on the local machine and leverages the cluster's computational power. The resource allocation for the Spark application is defined using several key flags. Num executors 4 specifies the number of executors worker processes to be launched in the cluster. Each executor will handle a subset of tasks for the Spark application. Executor memory 4G allocates 4 GB of memory to each executor, ensuring sufficient resources to process data without memory constraints. Executor cores 2 assigns 2 CPU cores to each executor, enabling parallel execution of tasks within each executor. Finally, the my underscore script.py argument points to the Python script containing the Spark application logic. This script is distributed to the uncluster, where it is executed according to the specified configuration. In summary, this command showcases how to run a PySpark application in Yarn mode, leveraging its powerful resource allocation and scheduling capabilities. By specifying resource parameters like the number of executors, memory, and cores, you can fine-tune the application to efficiently utilize the cluster's resources, making it a preferred choice for large-scale data processing in Hadoop environments. Kubernetes mode. For this example demonstrates how to run a PySpark application in Kubernetes mode, where Kubernetes acts as the cluster manager. Kubernetes is a modern container-based orchestration platform that provides dynamic scaling, workload isolation, and seamless deployment for Spark applications, particularly in cloud-native environments. The command begins with Spark submit. the utility for submitting Spark jobs. The master K8 SHTTPS Kubernetes API Server 443 flag specifies Kubernetes as the cluster manager with the URL pointing to the Kubernetes API server. This connection allows Spark to communicate with the Kubernetes cluster for resource allocation and task scheduling. The deploy mode cluster option indicates that the driver program will run within the Kubernetes cluster rather than on the machine submitting the job. This setup ensures that the driver leverages the cluster's resources and eliminates local machine resource dependencies, making it ideal for production environments. The application configuration is fine-tuned using conflags. Spark.executor.instances 3 specifies the number of executor pods containerized Spark workers to be created in the Kubernetes cluster. Each executor pod processes a subset of the data and contributes to the parallel execution of the application. Spark.kubernetes.container.image Spark-image defines the Docker image to be used for the Spark application. This image contains all the dependencies, libraries, and Spark binaries required to execute the job. By using container images, Kubernetes ensures a consistent and portable runtime environment across all nodes in the cluster. Finally, the my underscore script.py argument refers to the Python script containing the Spark application logic. This script is packaged and executed within the Kubernetes cluster with tasks distributed among the executor pods. In summary, this command showcases how to submit a PySpark application in Kubernetes mode, leveraging the platform's container orchestration capabilities. By running Spark applications in Kubernetes, you benefit from dynamic scaling, workload isolation, and seamless integration with containerized workflows, making it a preferred choice for modern cloud-native data processing pipelines. And that's a wrap on the different cluster managers available in Spark and their impact on PySpark applications. Each cluster manager, whether it's standalone, Yarn, Mesos, Kubernetes, or local mode, offers unique features tailored to different environments and use cases. By understanding their strengths and limitations, you can make the right choice for your data processing needs. If you found this video helpful, don't forget to like, share, and subscribe for more insights into Spark, PySpark, and distributed computing. Thanks for watching and see you in the next video.